I'm going to record it because I didn't record this. But all right, here's your next problem. Undo. So find the volume. And you guys are asking questions if you have any questions, right? Find the volume of the solid of revolution created by revolving the region bounded by y equals x squared, y equals 9, x equals 0 in quadrant 1. I just want quadrant 1. About the y-axis. So I want the region in quadrant 1 bounded by y equals x squared, y equals 9, x equals 0, revolved around the y-axis. And I want to know what is the volume of the resulting solid of revolution. Okay? We started talking about these last time, where we take a shape and we revolve. So I want y equals x squared, y equals 9, x equals 0 in quadrant 1, revolved around the y-axis. What shape are you getting? What does your cross-section look like? And I decided we're going nice and slow, so your exam that is supposed to be next week is not going to be till the Friday after break, okay, guys? We're just going to take it as we go, all right? I'm not going to push us to where we just spoon things into our heads. I want us to understand these problems. Love it. So I want to see on your paper a graph, and I want to see a solid. I want a graph and a solid. Show me the graph. It is like a U. 1 goes to 1, 2 goes to 4, 3 goes to 6. Then it's a U as well. It's also a U. It makes it a little, well, 2 would map to 16 instead of 4, so it would make it thinner, but it also makes it wider on the bottom. But this is more of just a parabolic shape. Nice. You got your area. It's this one in here, right? Beautiful. And then you're sending it about the y-axis. Beautiful. We got our shapes. I see our shapes. I see what's going around the y-axis. Nice. It's a solid, meaning it's like solid all the way through. And you guys are using a disk method, right? Because we talked about the disk method last time, meaning when we cut this thing, we cut it perpendicular to the y-axis. Nice. And when we cut it perpendicular to the y-axis, that helps us. That helps to see what our radius is. So we're going to set it up. We've got y equals x squared. 1 maps to 1. 0 maps to 0. 2 maps to 4. Ooh, Tina undid that. Undo that. Do it again. Let's try this again. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 goes to 1. 2 goes to 4. 3 goes to 9. You got a shape. Y equals x squared. Y equals 9. X equals 0. The area we're looking at revolving is here, right? It touches the axis, and my axis of rotation is the y-axis. So this guy's the one that I'm revolving around. Hey, Steffo, how are you? And so this guy, was it a good seminar, Jaden?
Wonderful seminar. It was all about my my social security, getting that up.
Oh, good.
I gave him my number. I gave him some advice too. It was a bunch of old people, so I was like, man, you guys need to be doing this younger. Like,
Yes, you do. Absolutely, you do. 1,000%. That's really smart.
I don't even know what job it is. I'm working on it.
You're very smart. Very smart. So we got a solid revolution. Everybody's got that solid revolution. So my first question is, these cuts. So slow down, Tina. Slow down, Tina. Right now, the only method we know is what's called, for volumes, if they're revolving, is something called the disk method, right? And the disk method is called the disk method because we're going to cut this shape and pull out disks, right? We're going to cut this shape and pull out disks. And when we cut perpendicular to the axis of rotation. And our radius for each of these disks is measured from the axis of rotation. I write this down because, again, we're going to learn a whole lot of methods, and it helps to keep it straight by writing down what's going on. In the disk method, we have an axis of rotation. We're cutting perpendicular to that axis rotation. And I love it. I saw, Angela, you got your R right here beautifully. R is that distance right there. It's a cut horizontal, perpendicular to the axis of rotation. On your test, when you go to set these guys up, the very first thing that I encourage you to do is figure out what you're integrating with respect to and what your limits are. If that's wrong, the rest of your problem is going to be wrong. I'm just telling you now. If that is wrong, the rest of the problem will be wrong because you won't get your right radius, you won't get your right variables, you won't get your right limits, okay? So your very, very, very first step is to make sure you know what are my limits of integration and what am I integrating with respect to. All righty, help me out here. Grant, what are we integrating with respect to? You know, don't you? Yeah, what are we integrating with respect to? dy. Why? How do you know it's dy? Because we're cutting along the y-axis. We're cutting perpendicular to the y-axis, so we're stacking things along the y-axis. So in the disk method, the axis of rotation matches the thing we're stacking along. It's the opposite on Friday, okay? So everybody's got it. We're stacking these disks so our axis of rotation matches dy. That gives me my limits. Hannah, did you get limits on these for me?
I got 0.
Yes, it is, because those limits come from the y-axis. Does that make sense? Carson, good. Everybody good. AK.
Are we doing top function?
I'm not stacking anything right now. I'm revolving. So, nope. In fact, my radius is, pardon? Let me see. Hang on, let me see. So, you're going faster than me. Hang on. You got such a brain. That is so cool. Alrighty. So, your radius right here is going perpendicular to the y-axis, and so it's this distance here, which is right side. I'm just going to put it off here to the left. I'm going to do a little think bubble. My little think bubble says my radius is the right side minus 0. But I have to change it in terms of x, so I have to solve for x. So my radius is square root of y minus 0, or just square root of y. So my radius, that distance, right, is, does everybody see that? You guys all got square root of y. You are my better class. I hate to say, don't tell them that, but you guys are performing better than them, and that's okay. It's not a competition. We're all here to win. We're all here to win. We're all here to succeed. We're all on the same team. But I think you guys got this, but help me out if you guys are stuck. You got square. Sometimes it's good to just feel good. So here we go. R is square root of y. Square root of y squared. Did you tell me y? Pi y? Is that what you said, AK? Did I integrate that right? Jake, did I integrate that right? Did I do that right, Lil? Or did I mess that up? I might mess it up. Did I mess it up? Everybody's good? No, that's not a trick question. I keep messing up. I keep throwing things where there's not supposed to be things. And should get 81 pi over 2, everybody, for this volume. But I'm going to slow down and stop because I went really, really, really fast. Step number 1, draw a picture. Write this in your notes if you want to. I don't care. Draw a picture. Look at it three-dimensionally if it helps you. If you see, is it solid? The region touches the axis, so it's solid. I'm going to choose the disk method, and in the disk method, I cut perpendicular to my axis of rotation. That axis defines what I'm integrating with respect to, which is dy, and it defines my limits, 0 to 9. What am I integrating? Circles? My radius runs opposite. My limits go up and down, but my radius is this distance here, which is outer function minus inner function, and that's square root of y minus 0, or just square root of y. That goes in there, and then we walk down. I'm stepping through this process because we're going to step it up a level. We're going to take these shapes and not just rotate them around an axis that's here, but maybe an axis that's over here. And we're not just going to have solids, but we're going to start making holes. Questions on this one? How are we? Everybody's good, right? Okay. Pardon? All right. Take the same shape. But send it around the x-axis. Still bounded, so this time I want to take the region bounded by, same region, y equals x squared, y equals 9, x equals 0, in quadrant 1, okay? I want it in quadrant 1. And I want it rotated about the x-axis. How many of you guys took Calc 1 before, like Calc AB or Calc BC, and remember doing these? Do you kind of remember? Some people kind of remember a little bit. Some people might not have, and that's okay. We're learning as we go. Question?
No.
Good. Okay. I'm just setting myself up here for success by drawing my picture. Setting myself up for success by labeling all my curves as well. So important. Identifying the region that's going to flip around and noticing that when it goes around the x-axis, I actually get like a, what do I get? Oh yeah, kind of, huh? Almost like an open book that gets flipped around, right? Revolved around. Somebody in the last class said, take like a solid wooden cylinder. Take a wooden cylinder and start drilling it a little bit with a drill bit, you know? And so you get this point thing in it, right? Can you guys picture that? Now, what makes this one trickier is it's not solid. So right away, I'm going to say to myself, this sucker is not solid. If it's solid, I can just use a disk to integrate it. It's not solid. In fact, it has a hole. If I was to cut it perpendicular to the axis of rotation, so if I was to slice it, are you with me, and cut it perpendicular to the axis of rotation and pull out that paper thin slice, are you with me? What comes out? This shape right here. Not a disc anymore. Do you see what comes out? Right? Because the outside is solid, the outer part is solid, but the inner part has a hole in it. This is called a washer. When your thing has a hole in it, notice I'll call it a gap. I'll call it a gap. See how there's a gap right here? There's a gap between your thing and the thing you're rotating it around. If that's the case, and you're deciding to use a washer or a disc method, you have to use a washer. And we already know what the formula is for a washer, don't we? Let me make this bigger. If I have a washer that's coming out, what's my formula for that area? It's pi times big radius squared minus pi times little radius squared, where big radius is the distance to the big part, whatever that is. And my little radius is my radius to the little part. Big R, little r. And I'll make him purple. Little r. Nope. Let's make him pink. Undo, erase. So big R is the distance from the axis of rotation in my picture. Oh, slow down, Tina. Undo. Slow down, Tina. Undo. First step. First step, because I want to get this problem right and I don't want to lose all credit. I want to make sure I set up my limits first, my bounds. If we are going to go around an x-axis and I am choosing to use the washer method, I am cutting it perpendicular to my axis of rotation, means I'm cutting it perpendicular to the x-axis, and I'm stacking them along the x-axis. So what am I integrating with respect to? dx? dx. Integrating with respect to dx. And what are my bounds, Grant? 0 to 3. Does everybody see why our bounds are 0 to 3? They have to match the variable that we're cutting along. So I have to match here, and 3 squared is what gives me 9, right? So I have to be going 0 to 3, okay? All right, now I got a couple points. All right, who cares if I mess up the rest, but I got a couple points under my belt. Now we have to put our formula in. Pi big radius squared minus pi little radius squared. Why? Why do I have that formula? Because I have a what? I have a gap. I have a hole. I have a hole. I have a gap. I have a gap between my region and the axis of rotation. Sweet. Now we find our big R. Our big R. Ooh, one more thing I forgot to write down. I'm going to put this in my think bubble because this is all in my think bubble over here. What else? R and little r are both measured from the axis of rotation. Most often it's the x-axis and y-axis. Sometimes it might be a different line. But the r values get measured from our axis of rotation. Okay, so here we go. I'm measuring from my axis of rotation right here. And my big R is... Jaden, you want to tell me what my big R is? You don't have to. You can consult with Carson.
The radius of it is 0 to 3 because...
Whoa. Slow me down. Stop a second. My radius, just watch me for a second, is going to go... All of these cuts are going to go from 0 to 3. Okay, but you see my circles. The radius is going to expand this way. It's going to go this way. Do you see it? Do you see it?
Oh, yeah.
Okay. How tall is that radius?
9?
It is. Is it always 9?
No.
Yeah, it is, because I got a straight line right there. Do you see that my big R is 9? Okay? 9, actually, if I want to write it down as a thought bubble, my big radius is 9 minus 0, top minus bottom. right? The top curve 9, the bottom curve 0. So my big radius really is 9 minus 0, or just 9, if I'm thinking of it as distance. And my little radius measures the gap. My little radius will always measure my gap. My little radius r measures my gap. Little r is this function minus 0. Okay, so what's that function? What's that function? X squared, but I'm integrating with respect to x. That works. Oh, sweet. I'm listening. Wait, go ahead.
Because like the basic shape, it looks like it's a disc, and then it's like a cone that comes inside. Because I'm not getting behind the whole washer idea. Like I ain't fun on it.
Gotcha. Understood. That's okay. Do you see this shape right
I
here?
see the shape. I just
Okay.
don't understand how
Do
it's
me a
like,
favor. Do me a favor, real fast. Let me do this. Ready? Hang on. We're going around the x-axis, right?
yeah.
And there's a hole, like a little bit of a hole, right? So if I cross cut, do you see that there's like a washer? Do you see? Well, not really. I don't know if you can see that.
It's just that like it looks like it comes in like a cone.
I wish I had my thing.
Because I see that it's like revolving around a circle, but like it's slowly getting smaller on every side.
It
so it'll
is.
be like a cone instead of another circle.
Good. It is. But what I want you to do, and I don't have, unfortunately, I left my thing at home. But if you, oh, no, that doesn't work. What if I cut it right? Okay, Lauren, you want to help me out here?
I was just thinking, like, it's kind of like the whole stacking idea, just with, like, subtracting instead. Like, those are, like, a whole bunch of circles stacked together, but instead of equaling in area, it equals nothing.
Because why wouldn't we just take like the disc and then subtract it by a cone? And
How
then just,
about
like,
this? How about this, Jaden? Let's take this shape here, are you with me? And separate it into two parts. Can you do that for me?
Yeah.
Okay, so what's left here is a little bit of this, right? Now, what's left over here if I take this part over here?
A
Now
bunch of
I've got
circles, but with,
I've got like an empty space in the middle. Are you with me, right? Now, what if I take and just make it smaller again, and make it smaller again, and make it smaller again? Notice what happens is I'm getting this shape, but it always has a what in the middle of it? A hole, right? So if I look at it from the top, if I look at it this way, it's a shape, it's round because it's rotating, are you with me? But in the middle, it's got this hole. Do you see? It's got this hole right here in the middle. Are you with me now?
So the little hole is always changing.
So the little hole, yes, is always changing, right? You got it. It starts out really big. In fact, that hole, that gap goes the whole way. But as you move down, it changes. Are you with me? And thank you. The top one always stays the constant, but that little one gets smaller and smaller. That's what this does. X squared tells me when x is 0, how big is that gap? That gap is 0. Are you with me? Yeah?
Yeah.
When x is 1, how big is that gap? It's 1 unit. When x is 2, how big is that gap? It's 4 units radius. Do you guys see? You guys see what's happening? So, sweet. So then we put in here x squared. Everybody's good. Everybody's got a volume for this. You went 0 to 3. Yes, sir.
I have a question about little r.
Ask away. Ask me about little r. Yep.
So will there ever be a point where the little r is equal to the big R at the final limit of 3?
In fact, yes, here. The big R and the little r will match at that limit. In which case, that slice contributes nothing, right? 0. It doesn't contribute anything to my volume at that particular moment.
So the little r will always be less than or equal to the big R.
Little r will always be less than or equal to big R. That is correct.
The outside function.
Always, big R is always the outside function. Good questions. You guys, thank you for asking questions because it's just going to get more complicated. I have to tell you, it's just going to get more complicated. All right, how are you guys on this? So we go 0 to 3 of 81 pi minus pi x to the fourth. Is that what you guys got? And did you pull out the pi and integrate? Oh, undo. So I get pi, integrate from 0 to 3 of 81 minus x to the fourth dx. And what'd you guys get? 81x minus 1/5 x to the fifth? With a pi in front? And that gives me what? Pi times 243 minus 243 over 5 minus 0. Is that what you guys got for cubic units? I think so. Something like that. Any questions? Stefan?
I did a little differently.
Oh, yeah. What did you do?
I'm not sure if it's right.
Okay.
So I split it up like this instead of like that.
You don't get the same answer as me.
No.
No. Because what you did, unfortunately, what you did isn't going to work. Because the shape that you gave me is something solid squared. So you gave me this distance squared. So you almost gave me a shape, I think, revolving. You gave me the shape that revolves around this line. Whether you realize it or not, you took and you cut it and gave me one solid circle. When you only have one thing being squared, you see what I'm saying? Maybe not, but you'll see as we move on. But what you gave me, actually, and you guys might have a problem that does this, but what you gave me was you gave me, and this is why it gets so confusing and so complicated, is you gave me this shape here, and you went this shape, you went this way, and you revolved, whether you realized it or not, around the line y equals 9. And when we cut it, we get pi r squared, one single radius squared. And your radius is actually this distance from the axis of rotation, which is 9 minus x squared. So by your method, I don't know if this makes any sense, but you actually gave me a different shape. Do you see what I'm saying, kind of? So the idea is, if it's a solid shape, there's a single radius, pi r squared. If there's ever a hole, we want two separate pi big R square minus pi little r. I love that you asked that question, because I'm telling you, this is where it gets confusing, because I'm going to say, send this around this, and everybody's going to be like, what? You just blew my brain out. So the idea is, you guys all blow your brains. Did it just like go like this? Everybody. So if a shape is solid, I want you to get in the habit of saying one radius, one circle. If I have a hole, I'm going to have two different radiuses. One there and one there. Got it? How are we? Yeah? Are you having fun? Okay. Yes, Grant, go. Question.
So if the big R will always be
measured perpendicular to the axis of rotation. So little r fills in the gap. That's the inside radius for my washer, right? I have a washer. Little r is the little one, and big R is the big radius, which measures to the outside of that region that we're rotating. But in any case, I have to set up I need to set up my integrals, because otherwise I'm going to get it all wrong. So I want to make sure, very first step is to make sure I'm integrating perpendicular to the y-axis, means I'm stacking them along. What'd you get, Chase? D what? dy, absolutely, dy. And I think I saw you had the correct limits. What'd you get for your limits?
0, 4.
Wait, hang on. 0, 2 cubed is? Yep, you got it. You got it. 0 to 8. 0 to 8. Absolutely. 2 cubed gives us 8. Yes, yes, yes. Notice this is where your brains get all mixed up because you're looking this way and you're looking this way. You know what I mean? I am telling you, how many of you guys need to take Calc 3? Some of you guys are taking Calc 3. It is so important. You have to be looking this way on Calc 3 and this way, right? You have to go all different ways. You have to take a cross section and be able to look at a cross section and go one step at a time. First thing is limits of integration. What am I integrating or cutting against? I'm cutting against the y-axis from 0 to 8. Now, what am I cutting? I'm cutting circles. How do the circles work? They work sideways. I'm cutting sideways. My radiuses go this way, perpendicular to the axis of rotation, and they're measured from that axis. So here we go. Ready? We got pi big R square, pi big R square minus pi little r square. That's what we need for each washer. That was not very nice, Tina. That was really sloppy. Pi big R squared. Here we go. So, little think bubble. What's my big R? What is my blue distance? It's what? It's outer curve minus inner curve. What is it? It's 2, isn't it? Big R is 2 minus 0, or just 2. My big radius is always 2 units. Beautiful. My little r. Do you see? I'm breaking it up on purpose because we're going to take the same shape, okay, if we have time, and we're going to send it around a different axis, all right? So here we go. R, little r. So little r is this distance here. Reese, did you get this guy for me?
Yeah.
Okay, what'd you do? Solve for x?
Yeah.
Okay. So first thing is, I know I have to write it in terms of y because I'm integrating with respect to y, right? And so then you solved, and so what did you get your little radius to be? Y to the 1/3. Cubed root of y, or y to the 1/3 minus 0, which is just cubed root of y. So I like y to the 1/3. I like it. I like it. That's my little radius. So then when you stick it in the integral, we get pi times big R squared minus pi times little r squared dy. I'm going to pull pi out front. And I'm going to rewrite 2 squared as 4. And I'm going to rewrite y to the 1/3 as y to the 2/3. Is that okay with everybody? And then we integrate. Oh, what? What do we do here?
Y minus 3y.
Oh, okay, alrighty. 4y minus...
3y.
Slow me down. Hang on. Y to the 5/3 with a 3/5 in front, right? Beautiful. 0 to 8.
32 minus 175.
No, I'm just looking at this because I swear I just did this problem in my last class. And I didn't get this answer.
I did. I see it now. I got it.
No, I know. But I don't know what we did last class. All I have to do is say, that 3 hours sleep is not doing good for me. Am I doing this right, guys? Okay, this is what I get too. I have no idea what I did in that last class. That is not good. Alrighty. So I get 32 minus 32 over 5 times 3. I did not get this last time. I don't know what I did last time. Oh well, I'll have to look at somebody's notes. We messed up. I did a ta-da for sure. We did not get this answer in the last class. Okay. Sorry, I know I did a ta-da in the last class and nobody stopped me. So we're going to have to figure out what I did wrong in the last class. I definitely messed up somewhere. Maybe I switched and nope, I don't know what I did. Oh my God, what did we do last class? Okay, all righty, here we go. Ready for the last problem. Any questions on this one? Any questions? Did you answer? Last one. Last one of this kind. If we have time then, we'll see where we're at. Then we'll go around a different line. If we can't, we can't. But here we go. Here we go. We got y equals 5x squared. Y equals 5x. In the first quadrant, that's what x greater than or equal to 0 means. In the first quadrant, go about the y-axis. Go about the y-axis. Did anybody have questions on the last one? You have a question? Yeah? Oh, you mean by slices? Well, the one thing that you're doing is you're not getting the radius. You've got a diameter. I think you have a diameter. That's the first thing I see off the top of my head. Is it looks like you have a diameter, not a radius being squared. That's the first thing I see.
Oh, no, I had the radius, but it was saying it was wrong.
Then I better take a look at it. We'll have to see. I do want to point out, if you don't have Desmos, when you do this, they're both hitting right at this point x equals 1, right? One of them is y equal 5x squared, and the other curve is y equals 5x. If you've done this enough and practiced this enough, you see that the blue line, that straight distance, is always going to be on top of that black distance underneath, okay? So your first step is to draw the graph and then picture it. What am I going around? What axis am I going around? And then what's my outer radius and what's my inner radius? Do you guys see people in the other class? In lab today? Tell them they need to send me a picture of their work from my class. I want to see what we messed up on. I definitely did something wrong. Don't know what it was. Not sure what I did last class. Lost something. Oh, maybe we did. Oh no, it could have been right. Sorry, Jack wrote it up. So I didn't write it up. It's okay. I didn't. It might be right. He wrote it up. Sorry. Got a good answer on this one now? Okay, good. Would you integrate with respect to y? Limits 0 to 5. Very nice. Definitely 0 to 5. Limits 0 to 5, right? Integrating with respect to y. Beautiful. Just going to draw my picture. Remember, on your second test, you get to bring an index card. So jot little important things down, right? If I'm using the washer method, my R's are measured perpendicular to the axis of rotation. Means they have to go perpendicular. You guys know, because you're engineers, a lot of you guys, or else you're mathematicians, or you're chemists and stuff. You guys understand perpendicular distances. Correct. Because it'll be under both of them, right?
So draw a picture, see the area space? So take from this axis of rotation all the way to the outside. What is the outside? This curve, the curve. It is. The inside curve is this distance. Yes, it is. 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 Good. Awesome. Grant, you good? Any questions? So we got a big radius and a little radius. The little radius is perpendicular. The big radius is also perpendicular. But the big radius measures to the outside curve. The little radius measures to the hole, the inside curve. And I know it's a washer method, so it's pi big radius squared minus pi little radius squared. And I know because I'm going around the y-axis, I'm integrating with respect to y, which means my limits are 0 to 5 pi big radius squared minus pi little radius squared. Beautiful. Good job. What's your big radius? So your big radius is the outside distance. You see what I'm saying right there? Put it up to 25. That's it. So you're changing. I'm looking at the wrong problem. Yes, it is. That's my little r. Yep. That's your little r. You got an answer, right? Yeah. 125 pi minus 5 halves pi. Let me see. Yay, I like it. Oh, I see. Careful, square that second one. Angela, you might have been right, and I might have been wrong on that second one. Let me see. When you did the square root, are they all in the square root? What's in the square root? So your equation is what? Right, okay. So when you write it, both of them. Let's see if we do this right. I got to be real careful about this, guys. Your big radius, the green radius, is the outer function, and the outer function is my squared. So it's x squared equals y over 5, or x is the square root of y over 5. My big radius is the square root of y over 5 minus 0, or just the square root of y over 5. My little radius is just y over 5 minus 0, or just y over 5. And so when I go to put them in my problem, big radius is square root y over 5 squared. I missed that. I missed that on you. I missed that with you. Reese, I think I just missed this with you. I missed it. Yes, sir. Oh, no, I'm listening. I shouldn't have those pies in there because I pulled it out. But you can tell me, ask me a question. Yeah? Almost. Let me see. Maybe. You went too fast for me. Let me see if yours matches me. Grant, you're faster than me, so I have to write it out. I have to write it out. Let me see. Here we go. 0 to 5. Inside, I get y over 5 minus
y squared over 25 dy. Right, is that good? Okay, good. And so then I get volume is pi times. Now I have to, well, okay. I'll integrate. That's 1/5 times 1/2 y squared minus 1 over 25 times 1/3 y third from 0 to 5. Put that out of my way. So that's pi times 1/10 y squared minus 1/75 y cubed, which gives me pi times 25 over 10 minus 125 over 75, right? Which goes down to, what is 25 over 10? 5 halves minus, and what goes into both of those? Quarters, right? 5 thirds. 15 minus 10, which really is 5 over 6 pi, if I did it. Did I do that right? Maybe, maybe not. And then y equals 5x squared, which we already have our curves. Let me rewrite our curves. That's x equals y over 5 and x equals square root y over 5. What happens? I'm going to blow your socks. Ready? What happens if I take it and instead of rotating around a y-axis, what if I rotate about the line x equals -2? Let's talk through this. Yeah, question, Reese.
Would that just like make it so that instead of like when you find your radius from like the y-axis, you just find it from x equals -2?
Absolutely. It takes and kind of takes that cup of ours, right, and stretches it out, right? Do you see what I'm saying, guys? It's stretching it out a little bit. So the shape that you get, how do I do it? I like to, when I get a shape, I like to mimic it across the other side and draw like a circle to put it together in my head, right? So can you picture, right, this shape? It's just like a cup that's expanded. So it's like almost like a funnel, a little bit of a funnel, right? Are you with me? It's kind of like part of a funnel or something.
Is it an open bottom?
It is an open bottom. It's a hole, right? Now, I'm still cutting perpendicular to the y-axis, right? Because I'm using a washer method. Still cutting perpendicular to the y-axis. And so my shape follows all the same setups. I'm cutting, yes, sir. Go ahead, Grant. Ask away. What was that?
There'd be 3 circles.
There will only be, when you draw it,
You would have the circle of the outside diameter, and a circle of the inside diameter, and then a circle of the whole inside stuff. Like the empty spaces.
actually know what you're going to do. There's a way outside diameter. Okay. All right, guys. So we're good, right? Now, we're making our little radius. Little radius. Is everybody okay with our picture, right? Stay with me. The little radius measures from the axis of rotation. It fills in the gap. Okay, my little radius is perpendicular to my axis of rotation. So perpendicular, are you with me? And we go from the axis of rotation to the inside function. That's my little radius, okay? Are you with me? So, and the big radius, let's just draw the big radius in. The big radius goes from that axis of rotation to the outside curve, and it's perpendicular to my axis of rotation. So, now, in our think bubble, what is that big radius? It's a distance. Okay, from right to left. It's a distance. It's the outer curve. What's my outer curve? What's my outer curve? What's my outer curve?
We're done.
Oh, no, we're not just done. We're not just gonna, are you kidding me? That is unfulfilling. That is like having a chocolate cake right there, and they say, you can take a bite, and it gets right here, and you say, no, sorry, we're done. You can't have that chocolate cake. Isn't that like, this is a chocolate cake? Don't you just want to, this is a chocolate cake? Huh? What's my radius? What's my big radius? What is that, guys? Tell me.
Y over 5.
It's square root y over 5. Thank you. It's square root y over 5 minus negative 2, right? It's square root y over 5 minus, it's right side minus left side, right? That's our distance formula. Distance is always between two curves, right minus left. The right curve is square root y over 5. The left curve is negative 2. That distance is square root y over 5 minus negative 2. Or if you like, you can visualize it. All it's doing is taking our old radius and adding 2 more units to it. Do you see how we expanded it? And our little radius, r, is, somebody help me out, somebody help me out. What's my little r? You got it, Laura? You got the little r? It's the y over 5 minus the negative 2, or if you like, y over 5 exactly, plus 2. It's y over 5 minus negative 2, which is just y over 5 plus 2. Right side minus left side. So when you go to integrate, you take big R squared, which is square root y over 5 plus 2, minus little r squared, y over 5 plus 2. And that would be the integral setup for that particular problem. Do you guys see it? Oh, so good. It gives me goosebumps. You gotta draw. I'm telling you, if you draw these in, it's going to help you, because the next time we come in, we're going to have donuts. We'll have donuts, and we'll talk about cylinders, where you get heights and radiuses and all kinds of funky stuff, and your brain's just going to explode. So make